Hi, I am Louie, and I'm presenting you the assignment 2.5G. We have a function here that is equals to x to the power 4 minus 5 times x cubed plus x squared plus 21x minus 18. And the first question asks us the domain. And the domain of this function, obviously this function does not have a restriction. So it belongs to our real number naturally. And as for the x-intercept, our audience missed the lesson on the intersection of a linear function and a quadratic function. So here I prepared a simple quadratic function to help understand what is intersection. So this point is an intersection since the graph meets the x-axis and the y-axis. But it does not necessarily need to meet to intersect with two axes in the same time. All it means is that this graph intersects with another thing that is related to the question. And in this case, it is x-intercept and y-intercept respectively. And for x-intercept, it means the graph intersects with the x-axis. So when it's x-intercept, the y value of the intersection is equals to 0. So we let the original function equals to 0. And we factored it out to get this one. And obviously, if it equals 0, then each of the term has a chance to be 0. So there are 3 different kind of answers. And as a result, there are 3 different kind of x-intercepts. And y-intercept is quite the same. We only need to change the constant value into y. And y equals, x equals to 0 this time. And we figure out the y value, we figure out the y-intercept, and that is the 0, negative 18. And we move on to derivative. And the first derivative, apply the rules of the power rule, apply the power rule and the rule of the constant, which is the derivative of a constant equals to 0. So we apply those rules to the original functions here, and we get this one easily. And we factored it out, and then we find the critical number. So the critical number is the root of the first derivative, and they represent a turning point of the graph, whether it's increasing or decreasing. And we get the answers based on this factored form. It's quite the same as this one. And so there are 3 different kind of critical numbers. And I think it will be more convenient that we continue here. That is the interval testing chart of the first derivative. And based on the critical number we figured out before, and there are 4 different kind of intervals, and we can easily sub some testing numbers into the original function to decide to the first derivative to decide whether it's positive or negative. So it represents whether the function is increasing or decreasing. So the result is listed here, and so the increasing intervals are these 2, and decreasing intervals are these 2. Then it's the second derivative. Second derivative, apply the same rule, which is the power rule and the rule of the constant. So yeah, it's pretty natural, and we factor it out. And in order to classify the critical numbers, we sub in the critical numbers into the second derivative to help us understand the concavity of these critical numbers. And so when it's positive, it's like this, it's concave up. And if it's concave up, then it means that this turning point is a local minimum. And vice versa when it's a concave down. So the turning point means the local maximum. And here I made a mistake, that is, so this one is positive and means the minimum, and this one is negative and means the maximum. And I will change it in the submitted assignment, but here I hope that you could forgive this slight mistake. And then it's interval testing for the second derivative. And the second derivative is deciding or testing or trying to figure out the concavity of this function. So it's still based on whether it's positive or negative. I mean, in terms of the second derivative. So we can get the result easily by sub in some testing numbers based on the intervals here. And we get the result. So when x is smaller than 0.069, it's concave up. And yeah, the follow is listed. And the result is here. Then we can move on to the graph. Oh, I'm sorry, I think I missed the point of inflection here. The point of inflection means when the concavity shifted from up to down or to down to up. So in this case, these two 0.069 and 2.43, these two are all points of inflection since the concavity all changes. And we can use all these things we just figured out to graph it out. So first and foremost is the intercept. We have x-intercept and y-intercept listed before, and they help us to graph. And in order to connect these dots, we should first figure out the end behaviors of the function, since it's a it's a function of to the power of 4. So the end behavior should, and the leading coefficient is positive, so the end behavior is like this, both positive. And in order to connect these dots, we might need the help of the local maximum and minimum. So it goes this way to the x-intercept, and it gets across the x-intercept because it did not the root did not repeat. It's a single root, and it continues to the local minimum and bounce back to the y-intercept, and it continues to grow to the x-intercept. This is also a single root, and it goes through it to the local maximum, and then the function goes down to the third x-intercept. But this case, this root appeared twice, so the function needs to bounce back up to positive again. So that is all for my presentation, and I hope you like it. Thank you. Bye-bye.